Welcome to part 2 of the IRIS tutorial. In the previous video, we formed an aggregate SED of the blazar PKS 112714 using data from NED and from file. We also filtered out unwanted photometric points and shifted the SED from the observed to rest wavelength. In this video, we will build user-defined models to fit this blazar's SED. We start the fitting session by clicking the fitting tool icon on the desktop. This opens up the main fitting window. There are 3 sections. The first is the Components section, which lists all models we add during the fitting session. Below, we have the Model Expression field, in which we can arbitrarily combine model components into a full model expression to fit the data. On the bottom of the window, we have a series of options. We can add, edit, and delete model components, define ranges in which to fit the data, freeze and thaw parameter values, save the model expression, and customize the fit. We see that the IRIS visualizer has changed. The model is plotted on the data as a red curve. By default, the fitting session starts with a power law. It has not yet been fit, which is why it looks so offset from the data. Below the main plot is a data to model residual, which we can view in dex units or on a linear scale. This is to help us visualize how well the model fits the SED. So let's go ahead and initiate the fit. We click Fit in the main window. This opens up another window in which we can choose the optimization method, fit statistic, and view the fit results. Let's click Start to see what happens. We'll keep the default fitting methods, Nelder-Mead and least squares. We can see that the model has moved closer to the data and the residuals plot and model parameter values have updated. Let's go back to the small fitting window and change the statistic to chi2 data var, which is the generic chi-squared statistic. We can see that the plots and the parameter values have updated, as well as our fit results. With chi-squared-like statistics, we can generate confidence limits on the parameter values in the Confidence tab. For example, let's calculate the 90% confidence limits on the amplitude and index for the power law model. We type 1.6 into input sigma, click Start, and wait. The lower and upper limits for the parameter values are calculated and then displayed. Now, looking at the SED, we can tell that a power law is a poor model for this blazar. It has been shown in blazars that the radio synchrotron emission can be modeled by a log parabola, and that the so-called big blue bump in the optical UV region can be modeled by a black body. So let's add a log parabola and a black body model to the components list. First, let's remove the power law from the list. We highlight the component and click Delete. Now click Add. There are 2 lists of models we can choose from. The first contains the preset models that come with IRIS, and the second holds custom tables, models, and template libraries imported by the user. For more information on importing custom models, please visit the IRIS user guide linked below. We will select the black body and log parabola models from the preset list. This list contains mathematical functions like Gaussians, logarithms, and exponentials, and a plethora of physical models like Bremsstrahlung radiation, recombination, and dust attenuation. So let's go ahead and add the models to the components list by clicking on their names. The components are numbered by their position in the list. Black body is first, so it is called by the term C1. The log parabola is second, and so it is called C2. Say we want to model the SED as the addition of the black body and log parabola. In the model expression field, we type C1 plus C2. Before fitting, we may want to edit the model parameters. We do this by highlighting the model component and clicking Edit. This opens up a new window with the model parameter names on the left and fitting options to the right. The spectral and flux coordinates of the parameter values are always in angstroms and photons per second per centimeter squared per angstrom. So for example, the reference position ref is at 5,000 angstroms, while the amplitude is initiated at 1 photon per second per centimeter squared per angstrom. The checked boxes on the right tell us that these parameters are allowed to vary during the fit. If we wish to freeze a parameter, we uncheck the fit box. The blue arrow below the fit box opens up a new window where we can edit the minimum and maximum values allowed for that parameter, as well as link it to other parameters. So let's say we'd like the reference position of the log parabola to be at 1 million angstroms. We type 1E6 and click Apply. Let's also edit the temperature for the blackbody function with an initial guess of 30,000 Kelvin. Before we start the fit, we can define the range of data to fit our model to. We simply click the endpoints of the range we want to fit. Note that we are not fitting the X-ray data, only the radio and UV data. Alright, so now let's fit the SED with our composite model. We'll keep the Nelder-Mead for optimization and select chi-squared for the statistic. Now we see that the fit has significantly improved in the radio and optical regimes. We can zoom in on the residuals plot to visualize how well the model fits the SED. Note that we could go back in and add more components or fit the X-ray data. Say we're satisfied with this fit. We click Save at the bottom of the fitting window to save the model in CDB format, which allows us to read the model back into IRIS at a later time. We can also write the fitting results to a text file by going to File and clicking Write Components to Text File and either selecting Active or All Components. A text file of the model components is shown here. Alright, and that's about the gist of it. You have learned how to fit a user-defined model to an SED using the fitting tools provided in IRIS. This concludes the IRIS tutorial. There are many more directions one can take to analyze and fit SEDs in IRIS besides the ways demonstrated in this video. For more information, please visit the IRIS User's Guide at cxc.harvard.edu/iris.